All right, hello everyone. So I'd like to consider a really important and interesting topic, and that's the motion of a system of particles. Now, in order to wrap our minds around this, I want to consider the simplest possible concrete example, and that's when we have three particles interacting with each other. Once we understand this idea in the context of three particles, we can extend it to any number of particles without changing the basic idea. So, simplest example, three particles. So let those three particles be the Earth and the Moon and the Sun. Okay, so now these three particles, they are interacting with each other through the gravitational force. Okay, so at this instant of time, the three particles are located in these positions. And at this instant of time, the Earth is exerting a gravitational force on the Moon, which is this guy, and the Earth is exerting a gravitational force on the Sun. And the Moon is exerting a gravitational force on the Earth. And the Moon is exerting a gravitational force on the Sun. And the Sun is exerting a gravitational force on the Earth. And the Sun is exerting a gravitational force on the Moon. Okay? So the first thing to notice is that we have three pairs of Newton's third law action-reaction forces. So one pair is the gravitational forces equal in magnitude and opposite direction between the Earth and the Moon. The gravitational forces equal in magnitude opposite direction between the Sun and the Moon. And the gravitational forces equal in magnitude opposite direction acting between the Sun and the Earth. Okay. Now, the next thing to notice is that the net force acting on each of those three particles is in general not zero, which means that in general, each of these particles is accelerating. Okay? Now, because the Sun is much more massive than the other two particles, its acceleration will be relatively small. Nevertheless, that acceleration is crucial to conservation of momentum. So an acceleration over time is a change in velocity. When the velocity of the Sun changes, there's change in momentum of the Sun. Or the net force acting on the Sun, acting over time, transfers momentum to the Sun. Okay? So when this Earth-Moon system and the Sun are orbiting around each other like this, then at this instant of time, the Earth-Moon system as a whole has some momentum in that direction. Later on, it's over here and has momentum in that direction. So there's been a change in momentum from this momentum to that momentum. The change is that way, which means that in order for momentum to be conserved, there needs to be a change, a corresponding change in the momentum of the Sun that way. And how is that change happening? Well, there's this net force in that direction. Acting over time changes the momentum of the Sun in that direction. Okay, so momentum is a strictly conserved quantity. It's exactly like, we have a block sitting on the table, and that block is initially in motion. So there's momentum stored in that block in that direction. Okay, but then through kinetic friction, that block slides and comes to rest. Has the momentum disappeared? No, it's just gone into the Earth. Okay, so as that block is sliding, the block exerts a force on the Earth in that direction. That force acting over time transfers momentum from the block into the Earth, so that the momentum of the block Earth system doesn't change. Momentum is always a strictly conserved quantity. Okay, so it's very important. So we've got each of these objects is accelerating. Okay, and so there are net forces acting over time on each of these objects, and so there's momentum being transferred all over the place. There's also net forces acting through displacements. All these objects are in motion, so there's net forces acting through displacements, and so there's kinetic energy being transferred. So the kinetic energies of these objects are changing all the time. And there's also gravitational field energy, such that the net kinetic energy plus the net gravitational field energy is constant, and so on. So what we're going to imagine is our three particles are isolated from the rest of the universe. So I'll draw like a big circle around our three particles like this, and we'll call that the total. Okay, so this total system of three objects is isolated. Okay, so isolated means that there's no energy coming in or out, which means the total energy remains constant inside. There's no momentum in or out, which means the total momentum remains the same. Okay, so the total of the three particles is isolated. Now, we're not interested in the motion of the Earth individually or the Moon individually. I mean, the Earth and the Moon are orbiting around like this, but then that system as a whole is orbiting around like this, so the Moon is undergoing a very complicated motion. We're not interested in the motions individually of any one of these particles. We're interested in sort of the average motion of this system of particles, the Earth-Moon system of particles. Okay, so we're going to take out of all three particles, we're going to take two of them, and we're going to call that our system. That's the thing that we're focusing our attention on. Okay, so this is going to be called the system. Okay, and that system will consist, it'll be the Earth-Moon system. So it'll be masses M1 and M2. So we'll call object number 1 the Earth. It has mass M1, and object number 2, that will be the Moon. It'll have mass M2. And so what we're interested in is the motion of this system of particles as that system of particles and the Sun orbit around each other. Okay, and so how do we describe that? So that's the topic of this motion of system of particles. Okay, and so this is the system, this is the total, and so this thing is external to the system. It's everything else. Okay, so the Sun in this example, this is going to be external to the system. So it is equal to the total, all three particles minus the system. Okay, so it's everything outside of our system that we're focusing our attention on. Okay, and so we have that because the total is isolated, we know that the change in momentum of the total set of three particles has to be 0. And so, but that change in momentum of the total is consists of two parts, the system and the external. So it's the change in momentum of the system plus the change in momentum of the external particles. Okay, so certainly the momentum of the system can be changing. As we just said, we've got this Earth-Moon system is, you know, they're doing this sort of thing, but while they're doing that sort of thing, they're orbiting around like this. Okay, and the Sun and that system are orbiting around each other. And so certainly the momentum of the system can be changing. Okay, it used to be this way, now it's this way. The change is in that direction. Okay, so the change in momentum of the system over, say, wait 1 month, the change in momentum of the system might be, say, in that direction. Okay, so then there has to be a corresponding change in the momentum of all the particles external to our system. Okay, and so that has to be exactly equal and opposite. So this is the change in momentum of the Sun. And what's causing that? Well, it's these forces that these two objects exert on the Sun. Those forces, that net force acting over time of 1 month, is going to change the momentum of the Sun in that direction. Okay, like that guy. And that's what allows the change in momentum of the system to be in that direction, so that the total momentum in our three-particle system remains the same, constant. Okay, so great. And so let's label these forces. So if this is object 1 and this is object number 2, then the gravitational force, this will be the gravitational force on object number 1 due to object number 2. This force will be the force on object number 2 due to object number 1. And these forces are equal and opposite, and these are forces that are internal to our system. Okay, but then there are external forces. Okay, so this force here is the, what do we want to call this? This is the external, this is the force acting on number 2 due to particles external to the system. That's that guy. And this is the force acting on particle number 1 due to objects external to the system. Okay, that's the gravitational pull of the Sun on the Earth. This is the gravitational pull of the Sun on the Moon. Okay, but then there are also forces, because the forces always come in action-reaction pairs, and we can't forget that. That's very important. This force over here is the negative of F1 external, and this force that the moon exerts on the sun is the negative of the force that the sun exerts on the moon. And it's these forces that are very important. Those forces acting over time allow momentum to be transferred to the sun, so that the momentum of our system can change in such a way that the total momentum doesn't change, because momentum is a strictly conserved quantity. And I should also say that we are observing the motions of these three objects from some inertial reference frame. So I'll just indicate that up here. So there's some inertial reference frame. Okay, and so we'll talk about that a little bit later. Okay, good. So let's focus on just this system. So we know that just based upon Newton's second law of dynamics, we know that the momentum of the Earth at this instant of time, I mean, the Earth and the moon are going like this, and that whole thing is moving around like this. There's some complicated motion. So the momentum of the Earth at one instant of time can be changing, and it's changing because there's a net force acting on it. The internal force F12 and the external force F1 external. So just by Newton's second law, basic dynamics, the time rate of change of the momentum of the Earth, particle number 1, is equal to the net force. So the sum of all of the forces acting on particle number 1, acting on the Earth. Well, what are those forces? There's an internal force, a force that's internal to our system, the force on 1 due to object number 2 in our system, plus there's an external force, okay, the force on object number 1 due to objects external to the system, namely the sun in this example. And we also have, let's write it down over here, we also have that the time rate of change of the momentum of object number 2, the moon, is equal to the net force acting on the moon, and that has two parts. One of them is an internal force, so the force on object 2, the moon, due to object number 1, the Earth, the other object in the system, plus an external force. So the external force on object number 2 on the moon due to objects outside of our system, okay, in this case the sun. Okay, so we've got that. And so, but our system is this object, and so we can define a system momentum, which is the momentum of the Earth and the moon together, the total momentum of the Earth and the moon together, so the system momentum. So we can then say, well, that means that the time rate of change of the momentum in our system, of our Earth-Moon system, well, that's equal to the time rate of change of the momentum of the Earth plus the momentum of the moon. Okay, so it's dp1 dt, it's this, plus dp2 dt plus that. So we have internal forces F12 plus F21 plus external forces F1 external plus F2 external. Okay? Now, it's very important to see that these forces, F12 and F21, while they are an action-reaction pair of forces acting between the particles within the system. And so F12 equals minus F21, and so these guys cancel out. And all we're left with is the external forces acting on the system due to particles outside the system. Here the particle outside the system is exerting this force on one of the particles in the system and this force on the other particle in the system, and so we add up both of those forces. So we get that vector plus that vector is a total force in that direction. Okay, that's the total external force acting on our system of particles. And so this is the sum of the forces external to our system. Okay, so we've come to a very important result, which I'll write separately up here. So it says that the sum of the external forces acting on our Earth-Moon system, which is the net force the sun is exerting on our system in that example. So the net external force acting on our system of particles is equal to the time rate of change of the momentum in our system of particles. So the Earth and the Moon are moving and they have momentum, and the total momentum is this P system. Okay, and that changes according to the action of external forces. Now, there is a very sort of trivial example of this equation, or case for this equation, and that is when the net external force is equal to 0. In that case, it says that the system momentum doesn't change, remains constant. And that would be the case where we just took the sun out of our system, and so then there's no external forces acting on our Earth-Moon system, and the only forces acting are the internal forces that act between the Earth and the Moon. And our system of particles would then be isolated from the rest of the universe, and of course, the system momentum would remain constant because momentum is a conserved quantity. What we're doing now is something interesting. What we're doing is we're allowing there to be particles external to our system. And then, of course, the system momentum can change. It doesn't mean that momentum isn't conserved. It just means that if the momentum of our system changes, then there must be a corresponding change in the particles comprising the rest of the system, such that the total momentum doesn't change. So the momentum of our system can change, but then the rest of the particles absorb that change in momentum, so the total is conserved. So this is still, of course, conservation of momentum. Okay, but what we really want to get at here is motion of a system of particles. Now, it's certainly true that the Earth and the Moon are doing this, and while they're doing this, they are orbiting, and they and the Sun are orbiting around each other. So it's a very complicated kind of motion. What we're interested in is not the individual motions of the Earth and Moon around each other, but is there some kind of an average motion of the system as a whole? Is there, say, a point in between these two particles that nicely moves around the Sun and nicely orbits around the Sun in simple elliptical orbits? Okay, ignoring the details of the Earth and the Moon as they go on their complex orbits around each other. Okay? Is there some kind of a way that we can describe the motion of our system of particles in an average sort of way? Okay, and so that's what we're going to get at now. And it has to do with this concept of position of center of mass and all that kind of stuff. Okay, so in order to get at that, what we do is we just rewrite this equation. Okay, we say, yes, the sum of the external forces acting on our system is the time rate of change of the momentum in our system. Okay, so that's the time rate of change of what is the momentum in our system. Momentum is mass times velocity added up for both of the particles in our system. So it's the mass of the Earth times the velocity of the Earth at some instant of time, plus the mass of the Moon times the velocity of the Moon at that instant of time. Okay, and then we go one step further here. The velocity of the Earth or the Moon is the time rate of change of the position of the Earth or the Moon. Okay, so we can pull out one time derivative, assuming the mass of the Earth and the Moon are constant. So this becomes a second time derivative of mass of the Earth times the position of the Earth, okay, plus the mass of the Moon times the position of the Moon, particle number 2. So this is starting to look like net force is second time derivative of a position, like an acceleration. What we're missing here is a mass. It should look like net force is mass times acceleration. So what we're going to do is a little tiny trick. We're going to define the total mass of the system, m, to be mass of Earth plus mass of Moon. Okay, and we're simply going to multiply and divide by this capital M. So we multiply the outside by capital N, well, that's a second time derivative, times the second time derivative of 1 over m times this stuff. So then the big M cancels out with the 1 over big M. And so now we have an m1r1 plus m2r2. Okay, now this looks like net force, external force, is mass times the second time derivative of something which has the dimensions of a position vector, right? Because the mass in the numerator, the two masses in the numerator, cancel with the mass in the denominator dimension-wise, and we have the dimensions of a position. So this is some kind of position vector, and it's a very special position vector that's given a special name. It's the position of the center of mass point. Okay, so let's talk about that a little bit. What is this RCM? So what we have is, this is our inertial reference frame, and at some instant of time, the Earth is here and the Moon is here, and RCM is a vector which points from the origin of our inertial reference frame to some point in the system. Okay, so let's redraw that over here in sort of a nicer diagram over here. Okay, so here is our inertial reference frame. And at some instant of time, the Earth and the Moon are located in some positions. Okay, so this is, say, the Earth. And we're drawing the Earth as being more massive. So the position of particle number 1, the Earth, is relative to the origin, is a vector that points from the origin to the Earth at that instant of time. We'll call that R1. Okay, that's the R1 here. And then the Moon at, say, this instant of time is, say, located over here. And it's, say, less massive, so we'll draw it a little bit smaller. So the position of particle number 2 at this instant of time, this R2 here, is a vector which points from the inertial reference frame to particle number 2 at that instant of time. Okay? And now this RCM is some kind of linear combination of R1 and R2. It's a vector which points from the origin to some point in this configuration of masses here. But what point? Well, let's take a couple of examples, first of all, just to sort of fix ideas here, sort of get the feeling for this. Suppose that these two masses, the mass of the Earth and the mass of the Moon, were equal. Okay, and so our situation looked like this, and they both had mass, say, little m. Okay, and here's the origin of our coordinate system. Then m1 and m2 are both equal to m. Big M is equal to m plus m is 2m. So RCM, in the case where the two masses are equal, is just equal to 1/2 R1 plus R2. It's the average of R1 and R2. So this is R1, and this is R2. The average of those two vectors is a vector that lies, or points to a point exactly halfway in between M1 and M2. And the center of mass point is located exactly halfway between M1 and M2. But suppose that M1 is bigger than M2. Then, and in fact, let's make it really big. Let's suppose that M2 is tiny compared to M1. Then that term basically drops out. Big M is basically M1. M1 over M1 is 1. And RCM becomes R1. So RCM is a vector which points from the origin of our coordinate system to some point along the line connecting M1 and M2. When the masses are equal, the center of mass point is there, and RCM points from there to there. If M1 is much bigger than M2, then the center of mass point is located closer to M1, and RCM points from here to here. So that's actually the real situation, because the mass of the Earth is more than the mass of the Moon. Okay, so just intuitively, all that's happening here is, you got like a seesaw or a teeter-totter, whatever those things are called, and you have, say, one, more massive person on one end, a less massive person on the other end, and you ask, well, where am I going to put the fulcrum so that this balances? Well, obviously not in the middle. It has to go over here, closer to the more massive person. Just like the center mass point between the Earth and the Moon is located closer, it's on the line connecting M1 and M2, but closer to M1. Okay. Now the idea is this is sort of our average point. So M1 and M2, the Earth and the Moon, are doing this complicated motion, but at any instant of time there is a point between the two of them, the center of mass point, and that's sort of like the average position. And it's the motion of that average position which is very simple. Okay, so let's sort of write this out and make that clear. Okay, you'll see why it's so simple here. Okay, so let's write it this way. So the net external force acting on our system of particles, so the sun is exerting these two forces, that net external force is equal to the mass of our system times the second time derivative of RCM. Like that. So this is net force is mass times acceleration. Second time derivative of a position is an acceleration. Okay, and we can also write this as, so this RCM point, so the Earth-Moon system is this. At one instant of time, the center of mass point is here, and then later on the center of mass point is here, later on the center of mass point is here. So RCM is the vector which points from the origin of our coordinate system to the center of mass point, and that point is moving around. Okay, so, and its velocity, the velocity of the motion of that center of mass point is the time derivative of the position of the center of mass point. So we can also write this as m times the single time derivative of the velocity of the center of mass point. Okay, So the velocity of the center of mass point, say, as this system as a whole is, and the sun are orbiting around each other like this, so the center of mass moves from here to here to here. The velocity of the center of mass is first here, then here, then here. So that velocity is changing. And the direction of the change in this example would be this way. First it was a velocity in that direction, then it's a velocity in that direction. The change is that way. Okay, and so that's the acceleration of the center of mass point. So that's equal to mass times the acceleration of the center of mass point. So now this is great. So this is what we were looking for. We were looking to describe the motion of a system of particles. Well, what does that mean? Well, inside that system, there's very complicated motions. We're looking for sort of a description of the average motion of that system, ignoring the details of the motions of the particles within that system. Okay, so at any instant of time, that system of particles has some configuration, and there's a center of mass point. Later on, there's a different configuration, the center of mass point. That center of mass point just moves. And what's beautiful about this is it says that the center of mass point moves exactly as if it is a point particle of mass equal to the total mass of the system, big M, under the action of the external forces altogether acting on that single point. Okay, and so it takes a complicated motion of the Earth-Moon system and looks at the average motion as a whole, and that's very simple. Just a point mass of mass big M moving under the action of just the external forces. Okay? And the important thing here to notice is that the internal forces play no role at all. They cancel out here. It's only the external forces that affect the motion of the center of mass point. Okay, so that's great. So let me sort of illustrate this result, this important result, in the context of this example, Earth-Moon system. I'll flesh that out a little bit, and then I'll consider another example. Okay? Okay, so what I want to do now is just sort of flesh out these equations in a little bit more detail in the context of our Earth-Moon-Sun system, so that it's really important that you understand clearly what this is saying intuitively. It's a very simple and beautiful and powerful result. Okay, so let's suppose that at one instant of time, the Earth is located over here, and say the Moon is located over here, and say the Sun is located over here. Okay. Now at this instant of time, there is a point in space lying between the Earth and the Moon that is the center of mass point of our system of two particles. And it lies along the line joining the Earth and the Moon, and because the Earth is heavier than the Moon, more massive, it lies closer to the Earth. Okay, so at this instant of time, that's the location of the center of mass of our system of particles. Okay? Now, how do we actually calculate that point? Well, we have to calculate that point relative to the origin of some inertial reference frame. Okay, so this RCM is a vector which points from the origin of our inertial reference frame to the center of mass point. Okay, so we need to figure out, well, what's our inertial reference frame and what's its origin? Okay, so lots of ways to do this, but sort of the simplest way to do it, the most concrete way to do it, is to think like this. Well, we've got, at this instant of time, the center of mass of the Earth-Moon system is right over there. So as far as the physics is concerned, it's exactly as if both of those masses, so a total mass, capital M, is located at that point in space. So then we can say, well, what's the center of mass of that mass of mass big M and the Sun? Well, it's obviously going to be a point that lies somewhere along the line connecting the center of mass of our system and the Sun. Okay, so it's going to lie somewhere along this line. And of course, because the Sun is a lot more massive than our Earth-Moon system, that point will lie, very close to the Sun. So it'll lie, like, let's say, somewhere like this. So this is the center of mass point for the total set of three particles. Okay, and if we attach a reference frame to this center of mass point, well, that won't be an inertial reference frame because that center of mass point, its velocity is changing, it's accelerating. Whereas if we attach a reference frame to this point, the center of mass of the three system particle, well, then that will be, in fact, an inertial reference frame. Okay, so we can make the origin of our coordinate system right there, the center of mass of the three particle system. Okay, and that will be an inertial reference frame. And then we say, okay, well, how do we calculate this RCM? Well, we take 1 over m times the mass of the Earth times the position of the Earth relative to this origin at that instant of time, plus, mass m2, the mass of the moon, times the position of the moon at that instant of time. So m1r1 plus m2r2 divided by the total mass of our system will be a vector then that points from this coordinate origin to the center of mass point at that instant of time. Okay? And then later on, the Earth and the Moon are doing this. They're orbiting around their common center of mass, and the whole system is moving like this. So later on, the center of mass point is over here, then here, then here, then here, then here. Okay, and so that RCM vector is changing. This is the trajectory of the tip of the RCM point. This is the average motion of the Earth-Moon system. Okay, and so that RCM vector will be changing with time. The time rate of change of the position of the center of mass point is the velocity of the center of mass point. Okay, and that velocity of the center of mass point in turn will be changing. The velocity is first in that direction, then in that direction, so the velocity is changing. If the velocity starts here and then is in that direction, well, the change in the velocity is in that direction. So in fact, this is the acceleration. The acceleration of the center of mass point is, so what's causing that acceleration? Well, that acceleration is being caused by the net external force. Okay, and so it's a, you take the force that the sun exerts on the Earth plus the force that the sun exerts on the moon. That's a total net external force acting on the system, and that's towards the sun, and that's causing the acceleration of the center of mass of our system towards the center of the sun, as the Earth-Moon system as a whole, is on some elliptical or circular orbit. Well, the sun and our system are elliptical orbits like this. So the Earth-Moon system is on a large elliptical orbit, and the sun is on a small elliptical orbit around the center of mass of the total system. Because remember, if the velocity of our center of mass is changing, the momentum of our system of our system of particles is changing. Well, the only way our momentum of the system of particles can be changing is if the momentum of the sun is changing, so that the total momentum of our isolated system remains constant. So the sun has to move, okay, in order to absorb the changing momentum of our Earth-Moon system as its average center of mass point moves around. Okay, so that's this is a really great example. So it's important that you just think this through and make sure all of this makes sense. I'm going to give you just another quick example of this. I'll just erase this and be right back. Okay, so I want to give you one more example, just sort of a qualitative example to help make sure you have a deep understanding of this really important result. And that's the example of an exploding projectile. So the picture is something like this. We've got the surface of the Earth here. And all we're basically doing is we are going to launch a projectile. This projectile is going to move on a parabolic orbit and land back down here if nothing happens, okay? So we're going to take as our system of particles the particles that make up our projectile. So our system, this is kind of like the Earth-Moon system, okay? And it has a mass capital M, let's say. Okay, and then this system is not isolated. It is interacting with another big particle called the Earth. Okay, so the total isolated system is our system here plus the Earth. Okay, so now it's certainly true that the external particle, namely the Earth, is exerting forces on our force on our system, which is the gravitational force, which is causing this particle to accelerate. The acceleration is always g, downwards like this, causing its parabolic trajectory. But at the same time, the system is exerting a gravitational force on the Earth, upwards like this. So the Earth is accelerating. Okay, and that's really important, so that when the momentum of the vertical momentum of this system changes, well, the vertical momentum of the Earth changes by exactly the opposite amount, so that the total momentum of our system plus external particle Earth remains the same, remains constant. Momentum is a conserved quantity. Okay, but the acceleration of the Earth, because the mass of the Earth is much bigger than the mass of our system, while the Earth accelerates, its acceleration will be extremely tiny. Okay, and so for all practical purposes, we can choose our inertial reference frame to just be the usual reference frame attached to the surface of the Earth. Okay, so great. That's the origin of our inertial reference frame, is the launch point of our projectile. Okay, so now what we want to do is, like, the center of mass of that system of particles, of that projectile, of course, is going to move from here. It's just going to move along this parabolic trajectory if nothing happens here, okay? So we want to sort of track the center of mass, the location of that center of mass point, and we do that with this RCM vector, a vector which points from the origin to the location of the center of mass point. Okay, so that center of mass vector, RCM, say at this instant of time, RCM is this vector. Okay, so that's RCM at that instant of time. Okay, but of course, that center of mass point is moving. There's some velocity. So this is VCM at this instant of time. And of course, that center of mass point is accelerating because that velocity is changing, while the acceleration of the center of mass point, well, that's just g. Okay, we're on the surface of the Earth with a gravitational acceleration g. Okay, so what we're saying is that, yes, the center of mass point is accelerating. What is causing that acceleration? Well, the net external force. The particles external to our system is the big particle called the Earth, and that's exerting an external force, gravitational force pulling down. And if we take that gravitational force pulling down, we divide by the mass of the object, well, we get the acceleration of our system, which is just acceleration of gravity like that. Okay, so that's all fine and well. And if nothing happened, then our projectile would just move along its parabolic trajectory, and nothing would be different from what we've talked about a million times before. But now what we're going to do is something interesting. We're going to say that, let's suppose that at this point in the trajectory, or right over here, let's suppose that our projectile explodes. Okay, so let's suppose that it explodes and breaks into two fragments. Okay, so we'll call this fragment number 1 and this fragment number 2. So during the explosion, as this projectile splits in half, there will be a force acting on fragment number 1 due to fragment number 2, and a force of equal magnitude opposite direction acting on fragment number 2 due to fragment number 1. So there are internal forces acting amongst the particles making up our system. The point is that those internal forces, they do not contribute, they have no effect whatsoever on the motion of the center of mass point. Okay? All that appears here is the net external force. The sum of the internal forces is 0, has no effect. Okay? So what's going to happen is the velocity of the center of mass point at, say, this instant of time was like this. So that means both fragments, the upper and the lower fragment, were just before the explosion moving in that direction with that velocity. But now there's a strong force acting for a very short amount of time, which causes an acceleration of particle number 1 in that direction. So the velocity of particle number 1 changes from this velocity to this velocity plus, say, some velocity, change in velocity in the direction of F12. And so the velocity of fragment number 1 immediately after the explosion is like that. And the velocity of fragment number 2 immediately after the explosion, well, before the explosion, its velocity was like this. It experiences a force in that direction. That force acting over time is a change in velocity. So there's a change in velocity in that direction, say this much. And so the velocity of fragment number 2 immediately after the explosion is, say, this velocity. Okay? So then, immediately after the collision, we have this fragment of, say, mass m1 with this initial velocity. And so it's just going to take off on this parabolic trajectory like this. And so sometime later, we'll have fragment number 1, which is of mass m1, somewhere along its trajectory, its new trajectory. And we're going to have fragment number 2 starts with this initial velocity. Okay, and so it's just going to move on a parabolic trajectory of its own, like this. Okay, and the point is that, say, at some instant of time, m1, fragment 1 has moved from here to here, and fragment number 2 is, say, moved from here to here. So this is fragment number 2. Okay, the point is that the center of mass of this m1, m2 system is located somewhere along the line connecting these two. And in this particular picture here, obviously we've got M2 is a little bit bigger than M1, so the center of mass point is located there. Okay, so the point is that these two fragments take off like this, and so our system becomes more complicated. Okay, but the center of mass of that system of particles will always continue to move along the original trajectory as if nothing had happened. Because what's happening here is what's causing the acceleration of the center of mass point, which determines the trajectory of that center of mass point. What's causing that is just the net force divided by the total mass. Well, the net force is, there's an external force, namely the force of gravity that this big third particle is exerting on M1. So there's an M1g force that's external on part of our system, and there's a force M2g, external force M2g. And when you add M1 plus M2g, add the total external force, okay, well that's going to just equal, so the sum of the external forces acting on the system, well it's just going to be M1g plus M2g. Well that's just the total mass mg. Okay, and so the external force is just mg, and that's equal to m-ACM. So the acceleration of the center of mass is always this ACM. The acceleration of the center of mass point, this acceleration of the center of mass point is always just g. Okay, so the point is that regardless of internal forces acting amongst the particles making up our system, the system as a whole continues to move as if it is a single point particle of mass big M equal to the sum of all the masses making up the particle, acted upon by the sum of all of the external forces. Internal forces are completely irrelevant. Okay, so then that allows you to just understand qualitatively what happens in this interesting case of a projectile that explodes, right? So this is a really important concept to understand. So I hope that this example of the exploding projectile helps to make clear, a little bit more clear, these really important equations. All right? Okay, so this idea of the center of mass of a system of masses, where is that point? That's a really important concept in physics. And so I want to give you sort of a simple, concrete example of how it is you calculate that. Okay, so what we're going to imagine is we have three masses. So let's see, we'll have a mass m sitting over here, and then we will have a mass, say 2m, twice as massive, 2m, sitting a distance l up away from little m, and then we'll add a third mass, which is 2l to the right. So 1l, 2l to the right. Okay, so here is a particle with mass 3m, let's say. So that is located a distance 2l to the right of our first mass, little m. So we've got this set of three masses, and we're wondering, well, where is the center of mass point exactly of that system? The equivalent question is something like this. If I have a massless plane here, and I put an m there, a 2m there, and a 3m there, the question is, where would I put my finger underneath in order to balance that? Okay? To balance that system of three masses. It's sort of like this. I've got two masses, and they're connected by a massless rigid rod here. Where do I put that, that fulcrum point in order to balance those? Okay? So if we look at, say, the mass 2m and 3m, we ignore this one for a minute, then where is the center of mass of those two masses, the center of mass point of those two masses? Well, it'll lie somewhere along the line connecting 2m and 3m, and because 3m is bigger than 2m, it won't be in the center, it'll be a little bit further over. Okay, so it's as if we have an object of mass 5m sitting right over there. And now we say, we've got an object of mass 5m there and m over there. The center of mass of that system lies somewhere along the line connecting little m to 5 little m. And so, but since 5 is bigger than 1, it'll be, closer to the 5m. So maybe something about like right there. So this is where we might guess the center of mass point to be in this system, okay, of three masses. Now, how do we calculate that? Well, in order to calculate that, we calculate this RCM vector. Remember that the RCM vector is a vector that points from from the origin of some coordinate system to the center of mass point. So if we chose the origin of our coordinate system to say be over here, then RCM, the vector we would calculate RCM would be a vector that points from here to here. If we were to choose the origin of our coordinate system to be over here, then RCM would be the vector pointing from this point to the center of mass point. The point is that the vector RCM, of course, depends upon the choice of the origin of the coordinate system, because by definition it points from the origin of the coordinate system to the center of mass point. But the key point here is that the center of mass point is independent of the choice of your coordinate origin. Okay, the center of mass point is just a point that depends upon the masses, not upon the choice of the origin of your coordinate system. Okay? So we can choose that point to be anywhere. And so, as usual, you think about it a bit, and you make a convenient choice. So let's, in fact, put the origin of our coordinate system right here. Okay, that's the origin of our coordinate system. And then let's take the x-axis this way and the y-axis this way, because it would be silly to put the x-axis this way and the y-axis this way. Okay, so we put the x-axis, say, in that direction, and we put the y-axis in this direction. And now we can calculate this vector RCM, which will point from the origin of our chosen coordinate system to the center of mass point, and therefore locate the center of mass point relative to our arbitrarily chosen origin. This is RCM. Okay? So how do we actually calculate RCM? Well, we just say the vector RCM. So what we did here was a sort of a special case with just two particles. So RCM is 1 over the total mass times the mass-weighted sums of position vectors. So RCM in general is, we can just generalize this thing. We just say it's a sum over the individual masses mi. I is an index that goes like 1, 2, 3. So this is m1, m2, m3. The masses mi times the position from our chosen coordinate origin to the mass in question, divided by, so for just two particles, it'll be m1 r1 plus m2 r2, which is this, divided by the total mass, which is the sum of the masses mi, m1 plus m2 plus m3. In this case, it was just m1 plus m2 because we had just two particles. So this is the general sort of definition of RCM. Works in one-dimensional space, 2 dimensions, 3 dimensions, for any number of particles. Okay? Let's apply this general definition of RCM to the case of 3 particles that we have in hand here. Okay, and so what is this? Well, we have to take a mass-weighted sum of position vectors. Okay, so I should also say that we're going to be writing out vectors. So this is I hat and j hat unit vectors. Okay. And so let's see. So what we want to do is in the numerator, we want to take mass-weighted sum of position vectors. So let's take, first of all, this mass. Let's call that mass m1. Let's call this mass 1, 2, and 3, or particle 1, 2, and 3, with masses m, 2m, and 3m. Okay? And so we go m, the mass of particle 1, which is m, times the vector which points from the origin to the location of that mass. Well, that's just 0, because mass m is located at the origin of our coordinate system. Okay? Plus the mass of particle number 2, which is 2m, times the vector which points from the coordinate origin to our vector, which is a vector of length L in the j hat direction. So that's L j hat, plus the mass of particle number 3, which is 3m, times a vector which points from the origin of our chosen coordinate system to particle number 3, which is a vector of length 2l in the I hat direction. So plus 2l in the I hat direction. And then we divide that by the sum of all of the masses. So that's mass m1 is m, mass m2 is 2m, mass m3 is 3m. Okay, and so RCM is equal to m times 0 is 0. So in the I hat direction, we have 2 times 3 is 6. So it's 6 ml in the I hat direction. In the j hat direction, we have 2 ml. in the j hat direction, divided by m plus 2m plus 3m is 6m. Okay, so 6m, excuse me, 6ml divided by 6m is L. So it's L in the I hat direction, plus 2m over 6m is 1/3 L in the j hat direction. So very good, that's RCM. Let's see if it makes any sense. So what it's saying is that to find the center of mass point in our set of three masses here, it's a vector which points from the origin to that point, and what it says is start at the origin and go a distance L in the I hat direction, which is halfway between here and here, and a distance 1/3 L in the j hat direction. So 1/3 L up in the j hat direction. And there you go. So our estimate of where it should be is actually borne out in when we do the calculation. Okay? So the key point here, remember that the center of mass point just depends upon the locations of the mass, just depends upon the set of masses you're dealing with. The RCM vector is a vector which points from your chosen origin of coordinate system to the center of mass point. If I had chosen, if I want to choose this point as the origin, RCM is this vector. If I had chosen this point as the origin, RCM would be this vector, okay, associated with a different origin. Okay. So that's a nice simple example of how you do this calculation. And this is the general formula. Okay, very good. Okay, so let me give you another example, illustration of the application of these really important ideas of, the motion of the center of mass of a system of particles under the action of external forces. Okay, and so this is the classic example of the person in the canoe. So it looks like this. So we've got a canoe, which is a boat. Okay, and that boat is sitting on the water. And let's suppose that there's no wind and the water is perfectly still. It's an idealized situation like that. And the boat can move freely on the surface of the water with virtually no resistance, no friction. Okay, and it's like sitting on a frictionless surface. And so we've got a person in this picture at the very left end of the canoe. And let's suppose that the person has a mass m1 and that the canoe has a mass m2. Okay, and so we have a system which consists of a person of mass m1 and a canoe of mass m2. And let's suppose that both are initially at rest. Okay, so at rest relative to what? Well, let's attach an inertial reference frame to the surface of the water. Okay, and now the idea is that this person is going to walk from the left end of the canoe to the right end of the canoe. Now, how does that person do that? Well, that person needs to accelerate to the right. There needs to be a force to the right. How does that happen? Well, the person pushes to the left with their foot on the canoe. So then the canoe accelerates to the left, the person accelerates to the right, walks to the other end of the canoe, and then pushes on the canoe this way, bringing the canoe to rest, and then the canoe pushes back on the person, bringing that person to rest. The point is that while the person moves to the right, the canoe moves to the left. Okay, so person moves to the right, person, while the canoe moves to the left. Okay, and so when the person gets to the other end of the canoe, well, the canoe has shifted over a bit. And so the situation afterwards looks something like this. The canoe has shifted over a bit. The canoe has shifted over a bit, and of course the person has shifted over. And now the person is at rest at the right end of the canoe, and the question is basically this. How far relative to the person's initial position has the person moved? Okay, so we'll call that D, and that's what we're really looking for here. Okay, so in order to figure out D using these ideas of center of mass motion and so on, we first have to think a little bit about the forces that are acting. So now, first of all, when you look at this situation, there are all kinds of vertical forces that are acting. There's gravity pulling down, there's the normal force of the water up on the canoe, there's the force of the canoe down on the water, etc., etc. So there are all kinds of vertical forces, but there are no accelerations in the vertical direction. So they all add up to zero, and we can just ignore them. So the first thing, when we're thinking about forces, we can clearly ignore vertical forces. And we'll focus our attention on the horizontal forces that are acting, while this person is moving from the left end of the canoe to the right end of the canoe. Okay, so let's consider what's happening when the person is accelerating towards the right. Okay, and the canoe is accelerating towards the left. So this is our canoe, and this is the surface of the water, and this is the person. The person has started accelerating towards the right. So the person is sort of like this and is accelerating towards the right. And so how does that happen? Well, the person pushes to the left on the canoe. Okay, so one part of our system exerts a force on the other part of our system. Force on the canoe due to the person is to the left, and then by those little atoms in the canoe get pushed to the left, they spring back to the right, and so there's a force of equal magnitude, opposite direction, acting on the person. So this is the force on the person due to the canoe. So F21 causes the canoe to accelerate to the left, F12 causes the person to accelerate towards the right. Okay, so very good. So there certainly are internal forces acting between the objects making up our system. Okay, but the sum of the internal forces, that's F12 plus F21, well, they just add up to 0. They occur in Newton action and reaction pairs, and so they add up to 0. So there's no net internal force on our particles. Okay, and that was important in getting this result. It was really the sum of all the forces, internal plus external, but the sum of the internal forces is always 0. Okay, so the point is that internal forces have no effect whatsoever on the motion of the center of mass point. Okay? The only thing that can affect the motion of the center of mass is mass point is possibly external forces. Okay? So now it's true that this canoe is moving to the left like this. And if there's water resistance, then the water, which is external to our system, can exert a force on one of the masses in our system, the canoe, in that direction, opposing its motion. Okay, but we're going to assume that this is virtually a frictionless surface. So there are no external forces that arise from the particles outside the system acting upon the particles inside our system. So we're going to assume this is virtually frictionless. And that tells us that all of the external forces, whatever they could possibly be, all of those external forces are basically 0. So we're going to assume basically frictionless. And that's a pretty good approximation in this case, and it will allow us to very easily apply these equations in a very nice way. Okay, so the fact that the net external force, the sum of the external forces, is equal to 0 has important consequences. First of all, it tells us immediately that the acceleration of the center of mass point is equal to 0. And if the acceleration of the center of mass point is 0, that tells us that the velocity of the center of mass point is constant. Okay, so if the center of mass point is moving, it moves with a constant velocity. Well, what constant velocity would that be? Well, it would just be 0 because everything started initially at rest. So that constant velocity of the center of mass is just equal to 0 in this case. Okay, so whatever the center of mass point is, it's not moving. Okay, and so it tells us that the position of the center of mass point relative to our coordinate origin there is constant. Okay, so when we look here and we see, well, what was the original location of the center of mass? Well, we've got a canoe with a mass m2. The center of mass of the canoe is right over here. Okay, and so effectively we have an object of mass m2 sitting here and an object of mass m1 sitting over here, and so the center of mass of our system of two particles lies along the line between here and here, and maybe the canoe is a bit more massive, so maybe it sits here. Okay, and so what this is saying is that the vector which points from our chosen coordinate origin here to the center of mass point, that vector RCM is constant. Which means that as the person moves to the right and the canoe moves to the left, it doesn't matter. The center of mass of that person-canoe system always remains at exactly the same point. And that's what's going to allow us to figure out what that distance d is that the person moves from their original position. Okay, so we set up the problem like this. In the initial situation, we've got a canoe of mass m2, which is effectively located at the center of mass of the canoe. So we've got effectively a mass m2 sitting over there, and we've got a person standing on the left end of the canoe. So effectively we've got a mass m1 sitting over there. And now we need to locate the center of mass point. Okay, so the center of mass clearly lies somewhere between here and here. Maybe if the canoe is a bit more massive, it's a bit further over towards the center of the canoe. So the center of mass point is there. But where exactly is that center of mass point? Well, the way we figure that out is we calculate RCM. So we need to first choose an inertial reference frame. Obviously, we choose an inertial reference frame that's at rest with respect to the canoe and the person. So we just are interested in the x component of that inertial reference frame. And then we are free to choose the origin of the inertial reference frame anywhere we like along here. So a simple choice, a nice choice, is right there, right at the location of the person initially at the left end of the canoe. Okay, and then when we calculate RCM, it will give us a vector which points from our chosen origin point here to the location of the center of mass point. So that's RCM. Now, of course, RCM is a vector. It has x, y, and z components, but clearly in this case the y and the z components are 0. We're just interested in the x component of the center of mass vector. We want to figure out what XCM is. And so how do we do that? So RCM in general is a mass-weighted sum of positions of the objects relative to O divided by the total mass. Okay, and so what we do is we start with, so XCM is going to equal mass M1 times the x component of the vector which points from the coordinate origin to mass M1. Well, that's just 0 by our convenient choice of coordinate origin, plus the mass m2 times the x component of the position vector which points from the coordinate origin to mass m2. So that's this vector. And so let's suppose that the length of the canoe is L. And so this is positive L divided by 2, half the length of the canoe. Okay, divided by the total mass, which is m1 plus m2. Okay, and so then this is just m2 divided by m1 plus m2 times L over 2. And so we can see that this ratio of masses here ranges between 0 and 1, and so clearly this is less than L over 2. It's between 0 and L over 2. Okay, and so it lies somewhere in between here. If the masses are equal, well then we'll have a mass divided by twice the mass. It'll be 1/2 of L over 2, or 1/4 L. It'll lie right in between. Okay, so that's right. And then what we do is we draw the final situation where the person is at the right end of the canoe, and we draw it in such a way that the center of mass hasn't moved. Okay, and so in this particular case, it's really simple. We can see it explicitly. Okay, so our final situation, this is the x-axis, as before. The canoe is shifted to the left and the person is shifted to the right in such a way that the center of mass of the person and the system has not moved. Of the person and the canoe has not moved. It's the same center of mass point. And so you can see, because in this first situation, the person is at the left end of the canoe, and in the second situation, the final situation, the person is at the right end, it's just flipped around. Okay, and so mass M2 has moved from the right side of the center of mass point to the left side by the same amount. So the center of the canoe will be sitting there. That'll be M2. And the person will have just, instead of being on the left end of the center of mass point, the person will be on the right end by exactly the same distance. So just to make these diagrams look nice. So it looks like this. So the canoe then looks like this. The right end of the canoe is here. That's the center of the canoe. And then the left end of the canoe is like this. So the left side of the canoe has shifted over like that. And the person has moved. This is now M1. The person has moved from this location, the coordinate origin. The person has moved from here to here. So this is the distance D that we are looking for. Okay? So now what we do is we calculate the center of mass. For this D here, we calculate the location of the center of mass, and we make sure that it's the same as the previous calculation. Okay, so how do we do this? So x center of mass, recalculated again in this new situation, is a mass-weighted sum of position vectors. And so we'll say mass m1 times the x component of the position vector pointing from coordinate origin to mass m1. Oh, well, that's just the distance d that we're trying to figure out here. So that's m1 times d plus m2, the mass of the canoe, times the x component of the vector pointing from the coordinate origin to m2. So that's that little vector there. Well, we know that the distance from here to here is L over 2. So the distance from there to there is L over 2. And the distance from there to there is equal to d. So the distance from there to there is going to be d minus L over 2. Okay, so this is a d minus L over 2. And then we divide by the total mass again, m1 plus m2. Okay, so now you look at this and you see, this factor of d is common to both. So it's an m1 plus m2 times d divided by m1 plus m2. Well, that's just d. That takes care of this term and this term. And what we have left over is just a negative m2 over the sum of masses times L over 2. Okay, now this answer for the position of the center of mass better be the same as this answer that we had previously. So this thing has to equal this thing. Okay, and so that tells us immediately that the distance d that the person has moved over is equal to this thing. Put the negative of that over to the other side. It's actually the same thing. The L over 2 just becomes an L. So we get m2 divided by m1 plus m2 times L. And so that's how far the person has shifted over from their original position when the canoe moves to the left and they move to the right. And so then we just make sure that this answer makes sense. Okay, so we consider, say, two special cases. So let's first take the case that the mass of the person is much less than the mass of the canoe. Okay, so we've got a super heavy canoe here and a super light person. Okay, so when that person is exerting forces on the canoe is exerting forces on that person. The forces are equal and opposite. But because the canoe is so much more massive than the person, under the same forces, the canoe will barely accelerate. So the canoe will barely shift to the left and the person will just easily move over to the right. And so that means that the canoe barely moves, and so the person should have moved a distance equal to L. In the limit that m1 is much less than m2, this should be L. Let's see if that's right. So if m1 is tiny compared to m2, we can drop this out of the denominator. It's m2 over m2, which is 1 times L. So that's right. Then we can consider the other extreme, where it's m2 that's much less than m1. Okay, so now the canoe is super light. It's just a canoe made out of paper. Okay, and the person is very massive compared to that. And so in that situation, and the canoe is sitting essentially on a frictionless surface. So what happens is the person just goes like this, and the canoe just slides without any effort. Just slides or has a large acceleration to the left compared to the person. So basically, let me say it more carefully, we've got forces that are equal in magnitude, opposite in direction. The person is very massive, so under that force, the person will barely accelerate to the right. But the canoe has a very low mass. Under that same force, it accelerates to the left a lot. And so what happens is the person basically stays in position, and the canoe goes zhook over like this. And so then the person doesn't move at all, but the canoe shifts all the way over its full length. And so we should have that this expression reduces to 0 when it's m2 that's much smaller than m1, or m1 is much bigger than m2. So if m2 is really small, okay, then in the denominator we can ignore it, but m2 is not. m2 in the numerator makes this thing go to 0. Okay, so that makes sense. Okay, and just I suppose as a final example, we could consider just sort of a concrete example. We can say, suppose that m2 is equal to, let's say, twice m1. The canoe is twice as massive as the person. What will d be? Well, in that case, d is going to be m2 is twice m1 divided by m1 plus twice m2, plus m2, twice m1, oops, plus twice m1, m2 is twice m1, times L. So this is 2 divided by 3 is 2/3 L. So if the canoe is twice as massive as the person, then when the person walks from the left end of the canoe to the right end, this distance d that they travel through relative to the original inertial reference frame is 2/3 of the length of the canoe, which is about this picture over here. Okay, so this is a really nice example of the application of this center of mass motion under the action of external forces. In this case, the external forces are 0, and so the acceleration of the center of mass is 0, and so the velocity of the center of mass is constant. In this case, it was 0, and so it's always 0, and so that means that the center of mass of that system of masses, regardless of the internal forces that are acting, the center of mass never moves. Okay, and it provides a nice way to solve problems like this. All right.